Hello everyone, I'm Jordan Cox and welcome to today's webinar, which is hosted by the National Renewable Energy Laboratory. Today's webinar is focused on the promise and potential of micro-reactors. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or over your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. If you choose to dial in by phone, please select the telephone option and a box on the right side will display the telephone number and audio pin you should use to dial in. If anyone is having technical difficulties with the webinar, you may contact the GoToWebinars help desk at the number shown on your screen. If you would like to ask a question, we ask that you use the questions pane where you may type in your question. Also, I want to emphasize that the recording of today's presentation will be added to YouTube and the link will be provided to you through your email that you can watch it at any time once it's been uploaded. Today's webinar agenda is centered around a presentation and panel discussion from our expert speakers on providing insights into the paradigm-shifting potential of innovative designs, new and exciting uses, and the timeline to deployment of micro-reactors. Before we get going, I want to say a quick thank you to all of our panelists who have joined us. And we have a very big panel today, so I want to say a quick thank you as well to all of our expert organizers. The admin and support who have helped with this webinar have made this possible, so thank you. In just a second, we will have our first panelist introduce the webinar, but first we are going to have a brief introduction of the Nice Future Initiative by Julia Visconti. Julie Visconti is a senior advisor with the Office of Nuclear Energy at the United States Department of Energy and leads country team member for the Nice Future Initiative. Julia, do you want to go ahead?
Thank you, Jordan. Hi, everybody. I'm one of the members of the Nice Future team, and I'd like to extend a warm welcome to everyone on behalf of the Nice Future Initiative lead countries team. That's the United States, Canada, and Japan. And our participant countries, Argentina, Poland, Romania, Russia, UAE, and United Kingdom. Being a part of the Clean Energy Ministerial, or SEM, is still new for the Nice Future Initiative. The Nice Future Initiative was formally launched last spring in Copenhagen in the presence of ministers. We will next be convening ministers in May 2019 in Vancouver, Canada. Stay tuned for high-level announcements related to the ministerial by checking www.cleanenergyministerial.org. Again, www.cleanenergyministerial.org. The initiative is off to a strong start and put, for the very first time, the spotlight at SEM on nuclear and high-level discussions about clean energy systems. Our Nice Future events have engaged a wide network of colleagues from 26 countries. Our events have also had collaboration or interest from more than 80 organizations. This includes governments, multi-government organizations, academia, industry, and NGO organizations, including environmental NGOs, groups supporting the engagement of women and millennials, and non-nuclear stakeholders from the renewable sector. The Nice Future Initiative engages all these clean energy supporters in new conversations about nuclear energy and opportunities for innovative nuclear to advance clean energy goals. The initiative considers the many roles that nuclear energy can play in future clean energy systems, including complementing renewable energy. It ensures that policymakers around the world have information on the full set of clean energy options. So today we are delighted to focus on one important and exciting topic of the Nice Future Initiative, micro-reactors. Micro-reactors have tremendous paradigm-shifting potential, as Jordan mentioned, and are one of the technologies to watch as part of clean energy systems designs of the not-so-distant future. Our webinars focus on specific topics that are part of the Nice Future vision. We want to share different country angles and experiences. To those who are participating on today's webinar, we invite your webinar or other suggestions to jordan.cox@nrel.gov. Again, that's jordan.cox@nrel.gov. If you like today's webinar, please spread the word. So to close this intro, let me say we are excited with today's experts and very much thank David Blee of the Nuclear Industry Council for proposing and co-organizing this webinar. Thank you, Jordan.
Thank you so much for that introduction, Julia. So in a moment, we'll hear from our first speaker who will give an introduction to the webinar, and that's David Blee. David Blee serves as the President and Chief Executive Officer of the U.S. Nuclear Industry Council, the leading business consortium advocate for nuclear energy and the promotion of the American supply chain globally. After David Blee's introduction, we will hear from Shane Johnson. Shane Johnson is the Deputy Assistant Secretary for Reactor Fleet and Advanced Reactor Deployment at the Office of Nuclear Energy in the United States Department of Energy. Along with Mr. Johnson, we will also hear from Jeffrey Merrifield. Jeffrey Merrifield is a partner and energy section leader at Pillsbury, Winthrop, Shaw, and Pittman Law Firm. After Jeffrey, we welcome Christina Bach to the webinar. Christina Bach is the Vice President of Nuclear Technologies and Materials at General Atomics. And finally, we will have Dr. Shannon Quinn. Dr. Quinn is Vice President of Science, Technology, and Commercial Oversight at CNL's Nuclear Science and Technology Projects and Programs for the Government of Canada, as well as commercial S&T projects and programs for third-party customers. With that, I will welcome David Blee to the webinar.
Okay, it's great, and we really appreciate the cooperation of the NREL, the quickly growing NICE Future team, and of course our all-star experts panel from North America. And this is a very dynamic and promising and very, very important topic. In terms of, and by the way, I understand this is a record turnout for the webinar series, and we're delighted to hear that and look forward to the Vancouver meetings as well that Julia talked about. As we look at the panoply of micro-reactors issues or challenges, or in terms of the future and the promise and potential, we certainly do that against the backdrop that shows certainly growing global demand, much and nuclear technologies across the board. We certainly have, why isn't that going forward? Hang on for a second. Okay, challenges worldwide, escalating global water stress throughout the world. And we have also a growing demand for electrification, as evidenced here by this slide on the electric vehicle penetration in the market globally. So given that those many challenges and certainly growing demand and growing electrification and the growing need for clean energy, we are fortunate that nuclear energy innovation is on the march, and the future of nuclear energy is now, as was opined by Georgia Power this past week, where they put the crown on the Plant Vogtle expansion, which was a capstone moment for the first AP1000 dome. In terms of other technology, we have enhanced SMR deployment on the horizon with NuScale small modular reactor closing in NRC approval, and other promising advanced reactor designs progressing in North America. Moreover, you have micro-reactor as sort of the latest manifestation of what we're calling a new era of innovation enlightenment, with myriad applications for global demand that we'll hear about here shortly. Obviously, one, economical clean energy replacement for diesel generation, off-grid flexibility, and versatility, including a nexus with renewable systems and industrial applications, response, to name a few. So for the next 25, 30 minutes or so, we're going to delve into this, and we will see SMRs are a game changer with respect to enhanced economics, factory assembly, versatility, advanced safety, and security. So with that, I look forward to our panel and to the question and answer session to follow.
Thank you so much for that introduction. We'll now hear from Shane Johnson.
Thank you, Jordan. My name is Shane Johnson. I'm the Deputy Assistant Secretary for Reactor Fleet and Advanced Reactor Deployment in the Office of Nuclear Energy at the U.S. Department of Energy. The Office of Nuclear Energy is the department's civilian nuclear energy organization, and we're really focused on three key areas with respect to the development and deployment of nuclear energy technologies. Those are supporting the existing fleet of commercial light water reactors that are in operation in the United States, the development and deployment of an advanced reactor pipeline for future reactors, those reactors being both light water reactor technologies as well as non-water advanced reactor technologies, and fuel cycle infrastructure related to the development and deployment of new fuel cycles in support of advanced reactors. Nuclear energy technologies have reliably and economically produced about 20% of the electrical generation in the United States over the last 2 decades. And nuclear energy remains the single largest contributor of non-greenhouse gas emitting electricity generation in the U.S. This represents about 60% of the non-greenhouse gas emitting electricity generation in the U.S. The Department of Energy looks across the spectrum of advanced nuclear technologies that are either in deployment or undergoing commercialization and look at it from the size comparison of its electrical output. And we've basically binned the suite of nuclear reactors across these 5 categories. Full-size reactors, which represent 92 of the U.S. Operating reactors in the range of something greater than 600 megawatt electric to 1600 megawatt electric. Mid-sized reactors, of which there are 6 operating in the United States currently. Those range in size greater than 300 megawatt up to 600 megawatt electric. Small modular reactors, we are characterizing those as something greater than 50 megawatt electric up to 300. And we currently have, as David pointed out, NuScale Power has their advanced small modular reactor under licensing review by the U.S. Nuclear Regulatory Commission, where they're seeking a design certification, which we are encouraged that will be coming in the not too distant future. The 4th category we see are very small modular reactors, and those range from something greater than 10 megawatt electric up to 50 megawatt. And several of the advanced reactor non-water technologies that the department is currently partnering with industry in the development would fall under this category of very small modular reactors. And then lastly, the micro-reactors, the topic of conversation for this webinar. Micro-reactors, the department sees as a class of very small reactors targeted for non-conventional nuclear markets, including remote sites, remote communities, mining sites, backup generation, possibly for nuclear power plants and other industrial applications. Such applications face economic and energy security challenges that can be uniquely addressed by these innovative micro-reactor designs. Generally, micro-reactors are differentiated from the other classes of reactors by features such as factory fabrication, transportability by truck, rail, and simplicity of design features, particularly those related to reactor control and safety. The department is very enthusiastic about the potential for microreactors to provide the industrial sector with clean, reliable, and resilient energy supply. These higher temperature, enhanced safety, and longer operating concepts are capable of electricity generation, district heating, industrial process heat, water desalination and purification, as well as hydrogen production. It is the department's view that microreactors can provide remote communities and industrial applications with reliable electricity at competitive prices compared to current costly diesel generator markets. They also provide resilient and reliable energy supplies and provide a source of clean and reliable electricity during disaster and emergency relief operations. Based upon feedback from U.S. industry, the department is undertaking key research, development, and demonstration activities in support of the commercialization of microreactors. The microreactor technologies are really based on reactor technologies that have been under development for a long time, and we're leveraging the historic research and technology that's been developed by the department and industry for non-light water reactors. Our research and development activities in support of microreactor commercialization has been focused principally in the areas of semi-autonomous and autonomous control systems, coupled with remote monitoring capabilities, improved materials and advanced manufacturing methods to reduce system costs and increase performance of the microreactors, as well as the development of approved transportation containers to aid in the deployment and the retrieval of microreactors from remote locations. The department has also been working with industry on the demonstration of microreactors before commercial deployment. We've been engaged by a couple industrial concerns looking to use our existing capabilities at the Idaho National Laboratory for testing microreactor technologies and concepts, as well as the demonstrating an entire working reactor before it is put into commercial use. The department is aggressively working to establish an inventory of fuel to support these near-term demonstration efforts. Microreactor designs are expected to be fueled with high-assay, low-enriched uranium, and the availability of this material on the microreactor development timeline is currently limited. The department has several efforts underway to make this material available on the timeline and schedules that the microreactor vendors are looking for in terms of supporting their demonstrations before commercialization. The department has also been supporting a new approach to licensing advanced reactors, including microreactors, through our licensing modernization project, which is a DOE industry cost-share effort to establish a technology-inclusive, risk-informed, and performance-based approach to licensing. The U.S. Nuclear Regulatory Commission has developed draft regulatory guidance based on this approach. And just recently, the NRC's Advisory Committee on Reactor Safeguards has recommended the Commission adopt this approach for non-light water reactor technologies. The department's been engaging with the private sector through private-public partnerships and accelerating advanced nuclear technology development, including microreactors. We have funding opportunity announcement that is open and available for industry to solicit funding from the U.S. government based on their reactor technology needs, whether it is from licensing support to technical support to working with our national laboratories. We're also engaged through our national laboratories and the nation's university nuclear engineering programs to provide both technical support to industry as well as developing the pipeline of talent that is going to be needed to push these technologies through commercialization and into long-term operation. And with that, I'll return the webinar back to Jordan.
Thank you so much for that, Shane. Now we'll hear from Jeffrey Merrifield.
Jordan, thank you very much. Let me pull up my presentation here. Again, as was mentioned, this is Jeff Merrifield. I'm a partner and energy section leader for Pillsbury law firm, and pleased to be here today to talk about the current state of what's going on with nuclear power. As we begin, we really
I'll just quickly jump in. It looks like you're in the presenter mode for your presentation, so it's kind of giving this dual screen view. If you could maybe back out of that and jump into the full screen mode, that would be great. Thank you.
Okay. That is a good question as to how to do that. Let me do a work on here. I apologize. Sometimes technology is...
No worries. We are just going to quickly take back control over here, and if you could select Monitor 2 when you do your presentation select, I think that might help, but we'll see what happens.
Yeah. Tell you what, once you guys you guys have a version of the slides, can you pull those up?
Yes, of course. We'll get right on that, bringing those up.
Okay. Actually, I pulled up Monitor 2. Can you see that now?
One second, we are just working through it.
Sorry about that. Well, folks, I apologize for the technical issue here. I'm actually...
Not an issue. Go ahead and select Monitor 2 from the drop-down. I think we just sent control of the presentation back to you.
Okay. Yeah, I'm trying to figure out how to...
No worries. We have your slides pulled up now. We'll bring it back to our screen and show your slides for you.
Okay, once you go to slide 2, please. All right, great. Sorry for the technical problem here. Really, where I wanted to talk about was sort of where it all began and how we got to the opportunities for microreactors today. And it really goes back to the individual on the right, Hyman Rickover, the head of our Navy nuclear program, who really initiated two things. One being the Nautilus, which was the first nuclear ship under sail. The second on the bottom was Shippingport Atomic Power Station in Pennsylvania, which really came as a development of that entire Navy program. The reason I start here is that, well, for the most part, all of the reactors around the world are light water reactors. Many of the advanced reactors and small modular reactors we're going to talk about today are not light water reactors. Some are, but many of them are not. And there are many developments that we've had in the U.S. Over the years where these technologies have been deployed, but certainly not as familiar to some on the line. Go to the next slide, please. There are, in fact, many innovative ways that nuclear reactors were deployed in the 60s and 70s. If you look on the left-hand side, for those of you who may not be familiar with it, the first nuclear reactor that we put down in Antarctica was to provide 1.8 megawatts of power for McMurdo Sound. So this is one of the first ways of generating power for the operations of the team who we deploy around 24/7 operations in Antarctica, and that was used for several decades as a very reliable source of that power. That was a 1.8 megawatt reactor, and actually this is the first modular reactor that was built in a series of 300,000 pound modules that were built and then shipped and installed in Antarctica. On the upper right-hand side, the closest nuclear plant to Washington, D.C. Was actually less than 20 miles south of Fort Belvoir. This was the SM-1 reactor of 2 megawatts operated by the U.S. Army. And if you actually flew over Fort Belvoir today, you can see that that reactor is still there and is to be decommissioned. On the lower right-hand side, one that is not as familiar with folks, the Sturgis. This was a converted World War II Liberty ship that had a 10-megawatt reactor installed. Both of those two were operated by the U.S. Army. In the case of the Sturgis, it was deployed to the Panama Canal for the purpose of powering several locks at the canal for, again, about a decade and a half. So a variety of what would now be considered micro-reactors deployed by the U.S. government in successfully demonstrating the capability of placing these reactors into service. Next slide, please. But a lot of the innovations that we're taking advantage of today were actually established by the Atomic Energy Commission decades ago. On the left was Peach Bottom Unit 1. This is a high-temperature gas reactor produced by General Atomics that used triso fuel in a hexagonal form. That led to several other designs that evolved from there, but really was the roots of many of the principles that we established in the U.S. for high-temperature gas reactors that will be certainly tapped into for future micro and larger advanced reactors that are proposed to be deployed over the course of the next 10 years. Similarly, EBR-1, which is a fast breeder reactor placed in Idaho. This was actually some of the first power that was produced in Arco, Idaho, sort of a very famous story of the first 4 light bulbs being powered by energy coming from this particular reactor that operated successfully for over a decade, and then subsequently was replaced by EBR-2, which has successfully run for a very long period of time. Finally, on the lower right in Tennessee, at Oak Ridge, the molten salt reactor experiment, 7.4 megawatts, also demonstrating the success of molten salt technologies. For the most part, many of these designs, because of the prominence of light water reactors, were set aside, but a lot of promising developments that occurred during the 60s and 70s. Next slide. Looking at the opportunities, it has been talked about before, the importance of nuclear power in both U.S. and international carbon-free generation. Certainly, advanced reactors and micro-reactors could play into that. As mentioned, micro-reactors typically are in the 1 to 10 megawatt range. And to add to some of the comments that Shane made, many of these designs are planned for load following and certainly will be complementary to renewable deployment that has already occurred here in the United States. Their small footprint, ease of use, allows for a number of additional deployment activities. Again, many of these conceptualized back by the Atomic Energy Commission decades ago. Next slide. In terms of where we stand today, there are a large number of advanced nuclear reactor developers. Third Way, a think tank here in Washington, has postulated that there could be at least 70 or perhaps as many as, it could be at least 50 or perhaps as many as 70 advanced reactor designs being deployed. Significant support by the U.S. Congress last year, $1.46 billion for the Office of Nuclear Energy. And a series of developers, we've had some discussions already about NuScale. I would mention X-Energy, which is the developer of a high-temperature gas reactor using a pebble bed technology, was a recent recipient of a $4.5 million DOE grant to focus on the production of those triso particle fuels that you can see in the right-hand side. Terrestrial Energy, a leading molten salt reactor developer, has received 3 GAIN grants for its design, and that is being produced in parallel both in the United States and in Canada. GE Hitachi's PRISM, that obviously is not a micro, that is a large fast reactor, but one which has been selected for the virtual test reactor deployment in Idaho. And then finally, Oklo, which is a micro-reactor, has been very active in its involvement with the NRC, my former agency, and they are actively moving towards having the NRC conduct a design review and are working on near-term deployment options in the context of the next 3 to 5 years. Next slide. As was mentioned, there are a lot of opportunities beyond baseload power. On the upper left-hand side, you'll see a picture of a diesel generator and tank farm in Alaska. If you look at this, there are a large number of those that are used in remote villages in Alaska. It requires the importation of very large amounts of diesel, or not the importation, but in transporting large amounts of diesel to these locations. That can cause some localized air issues. It can also be an issue if you have particular weather conditions that make it difficult to bring that fuel in. So the benefit of being able to tap into the 24/7 multi-year technologies provided by microreactors is certainly quite exciting. Other uses, now I have on the upper right-hand side one of the world's larger desalination plants, but certainly in remote parts of the world, there are areas which do not have access to clean, fresh water, and microreactors can certainly provide that type of technology to those people who need it. Finally, there are heat and power opportunities in a variety of petrochemical facilities worldwide. The use of clean nuclear energy through microreactors could provide an important benefit, not only from a clean air standpoint, but certainly from a clean energy standpoint. Next slide. And with that, I want to wrap up and thank all of you and look forward to any questions you may have.
Thank you so much, Jeff. And now we welcome Dr. Christina Bach. And to both Dr. Christina Bach and Dr. Quinn, I think at the beginning I messed up your titles just a little bit, so please feel free to correct those. We are very grateful to have you and want to make sure those are correct. But with that, I'll turn it over to you, Dr. Bach.
Okay, let's see. Do I have the screen there? Okay, I'll try and go pretty quickly through here so that we can maybe make up a little time so there's time for questions. I'm very pleased to be speaking here. I was asked to really give a talk about the technical considerations developing microreactors. So this will be a little bit different, and I'll try and go into where the technologies and the innovation and how it relates to nuclear energy sources really comes in. So I'll start with a little overview and then go into some places where we think the technology and innovation can change our future. So first, I just want to give an overview of the basic components of a nuclear reactor so that you can see exactly where the innovation can be happening here. So, basically you have fuel. It generates the heat. The coolant transfers the energy from the fuel to the turbine. The turbine converts the heat to the mechanical energy, and the generator finally converts it into electrical energy. So you can see on the right there, the inside of what Jeff Merrifield showed, which is the vessel of the shipping port reactor. So you can see the size there, and that picture is, you can see, dated by how the people look there. That's from 1956. And so the point here is that these four basic components are in any nuclear reactor, whether it be 1 gigawatt or 1 megawatt. And so let's just look a little bit more at that. Let's see, my advance button is not advancing. There we go. So if you look at a large power plant, this is Diablo in California, and on the bottom right there, you can see the turbine generator hall. And I put a little green bar there, which is actually right next to a person standing there, but he's a little bit small, so I just wanted to point out a size to give you an idea of how big these generator halls are for these steam turbines. Now, when you look at the technology, if you look at shipping port, for instance, the transfer medium was water, and so that water needs to be turned into steam. That steam then drives the turbine. And for a 1 gigawatt or 1,000 megawatt plant, it gets quite big, as you can see. So now with the understanding of nuclear energy today's new science and new engineering, now we can really design reactors for the application. And so if we look at now the kind of power level that we're talking about for microreactors, 1 megawatt is about 1,000 houses. So small modular reactors can be smaller. So, you know, in fact, an advanced reactor for a 1 gigawatt size from designs that we have at General Atomics can be about half the area that a typical plant takes up now. So as you can see, for small modular reactors and for micro, that's a much smaller footprint. And there's some things in the balance of plant that do not scale, but you can see that there can be a huge savings in terms of the size of the plant. So in the next view graph here, I just go into some of the micro-reactor characteristics from the point of view of a 1 to 10 megawatt plant. So obviously you have to be safe. So defense in depth means that you have multiple layers of safety. There are typically 3. We would still retain that in a microreactor. And passively safe has become more and more understood and important as we go forward in the future. So the new designs really focus on a compact reactor core to make sure we achieve this passive safety and still provide the power, albeit at a lower total power. The transportable nature is so that it can be taken to places where, for instance, there are hurricanes or natural disasters where you might need electricity very quickly in a populated area, or in very remote areas, as has already been discussed. So part of the transportable is that you want to have a very straightforward installation. So that doesn't need to be the number of years that you would take for a large plant, because much of this, as you can see at the bottom, would be modular and factory built. So there's an advantage there in terms of being able to control the cost of the fabrication, not just in terms of size, but also in terms of security and safety. And finally, we've already talked about the power being less than 10 megawatts electric, and that also enables you to be load following and matching with renewables, for instance. So if we look at a reactor designed for the purpose, a compact reactor core is going to need the following things that I have listed here, and I'll just talk about them very briefly. Many of the designs go to higher density fuel or higher enriched fuel. That allows you to get in a smaller volume a sufficient amount of fuel so that you can achieve the chain reaction and the fission reaction so that you can generate the energy. The next two there, the new and safer fuel rods, refers to the kinds of new materials that we use. For instance, as a stepping stone, you can think about the accident-tolerant fuel that's being deployed, or that is soon to be deployed for light water reactors. Those are different kinds of metals like Ficrol or ceramics like silicon carbide composites. These have different properties and interactions with the coolant. In the light water reactor case, it's water, but in an advanced reactor, that could be a different coolant. As you can see, I list there below, non-water coolants, which are like helium, molten salt, sodium, and lead bismuth. And that's in recognition of the fact, as Jeff Merrifield pointed out in the shipping port, I didn't go through that fully since he talked about it already, but the important point there is when you're designing a naval reactor, you have a lot of water around. But when you design a microreactor where you may be landlocked, you may not have the advantage of having a large body of water. So that's why these non-water coolants make siting much more flexible. And there are many advantages because, for instance, these coolants don't go through a phase change in the same way that water does, which is part of what contributes to the problems that we had at Fukushima. Another important part is advanced engineering and manufacturing methods. You can start. Whoops. Can you still hear me?
Sorry about that.
Right.
There was a little technical difficulty. Go ahead.
Yeah, okay. So the manufacturing methods, and you know, you probably heard things like 3D printing. Those kinds of things are starting to be applied to reactor components. Now, in terms of power generation, that's kind of the second half of the equation. And here, for a small micro-reactor, you can be smaller and much more nimble. And that's what allows you to be able to load follow much more easily, because there's less just physical inertia of the turbine, for instance, to get it spinning and follow the base load energy as it changes with renewables coming on and off the grid. And of course, there are advanced controls. And if it seems like that's not very interesting, I'll just give an example of natural gas plants. And you can see here that there's continuous innovation that has happened in, for instance, natural gas. Light water reactors have been around for over 30 years, and there are many technologies that we can take advantage of in the same way that natural gas plants are doing here. So of the two key enablers you see there, the advanced high temperature materials and the advanced manufacturing, and since 2000, they have gained efficiency of up to 22%. That would be huge to employ those kinds of advantages in a nuclear reactor today. So I just want to give some now overview, and this is taken as an example from EM squared just for simplicity, because it lists out kind of all the different areas that you can make innovation and advantages. So in this half, it's kind of the heat generation that I talked about. So you can see there's the convert and burn physics that has to do with how long your reactor can last. These typical micro-reactors can go from 3 years or longer. There are different reflector materials you can use to make the core more efficient at retaining those neutrons inside to keep the fission reaction going. High density fuels, as has already been talked about, uranium carbide, uranium nitride. Those have more uranium per volume, as well as being able to increase the enrichment. And then you have some things like silicon composite cladding, which are new cladding materials. The second half is kind of the power generation side, and you can see here the things that could be employed in an advanced reactor: high temperature gas turbines, variable speed permanent magnet generators, frequency inverters, dry cooling, etc. So I just wanted to give you a flavor of the kind of technologies that can be brought to bear to really bring the nuclear energy into the 21st century and enable small micro-reactors to be built. So with that, I'll leave you with questions and any comments. Thanks.
Thank you so much, Dr. Bach. And now we will hear from our final speaker, Dr. Quinn.
Hello, and thank you very much. If you bear with me, I'll present my screen. So for the sake of time, I will, I think, be able to progress quite quickly through my slides because my topic today is really sort of Canada's view of SMRs, and which would include the full range, including right down to micro-reactors. But as I have the advantage of going last, I also have the advantage of seeing that so Canada's position and strategic approach is quite well aligned with that of the U.S. And I think the audience will be able to see that what I will say now is very consistent with what we've heard from Christina, Jeff, and Shane so far. And so what I'll try to do is actually sort of point out where the similarities exist and maybe where there are some sort of slight differences that maybe we can all leverage for our respective advantage. Like the U.S., Canada has a long history in nuclear energy, dating all of the way back to World War II and our linkages to the Manhattan Project. Where we diverge a little bit in nuclear history is that then following World War II, Canada made a very conscious effort to pursue only civil applications of nuclear energy for really power and medical purposes as opposed to weapons purposes. So we are the only Tier 1 nuclear nation that is not a weapons nation, which puts our areas of technical expertise, places them a little bit differently than some of the other countries. But it puts us in a world where I think we can probably work with others to leverage our respective technical advantages in the area of nuclear. So one of the other things that I'll mention is that like the US, we have a very strong nuclear regulator and regulatory regime. What is maybe a little bit different in Canada is that our nuclear regulator, the CNSC, takes a non-prescriptive approach. And so while in Canada today we have heavy water reactor technology deployed, the regulatory regime is not really specifically tailored to that, but is built generically on the concept of being able to prove a safety case. And so from that perspective, it's quite well suited to being able to, from a regulatory point of view, consider new and novel technologies, which is one of the important aspects of being able to ultimately get some of these new and advanced reactor concepts to market. There we go. And so really in Canada then, because we do have a long history of developing reactor technology, it does position us well sort of alongside our nuclear regulator as being able to look at some of these advanced technologies and ultimately help the private sector bring these technologies to market. Because we do recognize here in Canada that the nuclear industry has changed quite a lot over the last many years, and the role of government in particular has changed. So today, it really is a global commercial market, one dominated by private sector entities and not one dominated by governments, which is as it should be. And so what we see going forward is that in Canada, we see the private sector leading this push into new and advanced reactor technologies. And of course, governments at all levels of government have a role to play, but they are not the leaders. They play an enabling role. So in Canada, we see that the SMR market is very ripe for Canada to take advantage, and really in two different roles, both as a buyer and an incubator. So in Canada, we see that we have many remote communities. There are 200 off-grid communities across Canada, as well as a significant mining and oil and gas market that is off-grid, and all of these have potential to be interested buyers. But we also have, as I said, an environment where we, as a hub and an incubator, to help the private sector bring these technologies to market, which is actually very similar to what we heard from Shane earlier in terms of the US DOE's approach to bringing to bear some of its expertise as well as some of its US DOE sites to work with the private sector. So what I can say is that in Canada, we've, together with CNL, we've put quite a lot of effort in trying to understand the market and specifically the market's interest in Canada, and we've had considerable interest. So dating back to 2017, when there were 80 responses from a variety of stakeholders to a market survey, all the way to today, where we have with CNL a formal invitation process to site a demonstration reactor at an AECL site. And in the first go around, there were 4 applications received. And I'll skip really, for the sake of time, right up to kind of where we are today in terms of CNL's invitation process. And that is to say that there are various private sector companies so working their way through the particular process. It is set up so that these different companies can work at their own pace. And what we see is that their StarCore and Terrestrial have passed stage 1 and invited to apply to stage 2. And then we have Global First Power passing stage 2 and moving into a stage 3, which really just goes to show that there's a broad market interest in demonstrating, I would say, in North America, broadly speaking. So Canada also went through a broader engagement where it looked at all levels of government, or various utilities and provinces and territories, to put forward a roadmap. So I would invite people who are interested to look at those, at that roadmap that is available online. And it had findings across 4 pillars. But really what came out was that that there is real opportunity for SMRs, yes, in Canada, but we think across North America, and importantly as a global market, and that SMRs really can compete with other electricity generating options. But one of the things that maybe I would like to reinforce, that's already been mentioned by some of the other speakers, is that SMRs also have an opportunity to work alongside other electricity generating options, particularly intermittent renewables such as solar and wind. But we do think that time is of the essence here, because there are climate change drivers that are creating an urgency. And in fact, there are many companies and countries outside of North America that are aggressively pursuing this. And so the window of opportunity really is now, if North American companies are to gain a certain competitive advantage in what we think is a global commercial market. So thank you very much.
Thank you so much for your presentation. I'll quickly say thank you to all of our panelists. We are now in the question and answer section of this webinar, and we received so many great questions. I want to just quickly note that we won't have time to get through all of the questions because we received so many of them, but we will do our best to reach out to our expert panelists and try to get the answers back to you. So we have them written down, we have them recorded, and we want to just thank everyone who submitted a question. So in the question and answer session, the first question that I think we'll start with is comes from multiple webinar attendees, is about the role of the Nice Future Initiative in all of the things that our panelists have discussed. The Nice Future Initiative is an international collaboration effort. And so I guess to all of our panelists are welcome to reply to this. What is your view of the role of international collaborations and initiatives like the Nice Future Initiative and others in nuclear technology?
Well, this is Tina Bach. I'll start off since there's a little gap there. You know, I think that all of these challenges are tough problems, and we should really all work together and try and move the whole industry forward. So, you know, international collaborations, I think, are important where they make sense. And, you know, this is a global issue, not just the United States or Canada. So, you know, overall, I think it's important to be collaborative.
Yeah, this is Jeff Merrifield. I agree with Tina, and I would add, I mean, I think what NICE really represents is a swing in the view toward how we engage in the use of energy technologies, both to enrich lives, spur economies, but also do it in a way which is clean and respectful of obviously the environment and the planet. I think for a long time, a lot of folks who were very in favor of the introduction of renewables and power storage to address those issues, and who were concerned about global climate change, really were focusing more on those technologies than looking at the bigger picture of how can we use available resources, including nuclear, to effectuate those goals in a more holistic way. And so I think the NICE initiative has done a great job of refocusing that to say, hey, listen, today, 35% of the world's clean energy comes from nuclear. How do we further enable these nuclear technologies in such a way to both provide more power and energy for economic growth and development in the third world and elsewhere, but do so in a way that really takes advantage of nuclear's clean generation portfolio? And I think the discussion today has really brought out that convergence of how that policy initiative undertaken through NICE, combined with the developments in both microreactors and advanced reactors, really gives us a springboard for full use of these technologies going forward.
Yeah, it's Shannon, and I think I would entirely agree with what's been said, and maybe just to say it slightly differently, it's been Canada's experience that in order to move towards clean energy across the board, it does take all forms of energy generation. And so while nuclear has to be cost competitive with other forms, it doesn't mean it's in direct competition. And in fact, we think it takes all of them working together. Part of the challenge that we've seen, at least in Canada, is that the nuclear conversation tends to happen within the nuclear community. And one of the things that the NICE future does as part of the broader clean energy ministerial is it brings the nuclear discussion into the broader discussion on clean energy with all of our colleagues across all of the different forms of energy generation, which is where we think it's properly placed, so that we can look to all of our energy colleagues to come with ideas on how all of the different forms of generation can be brought to bear to solve some of the climate change issues.
Thank you very much for all those thoughtful responses. So we are coming up on the end of the webinar, and we had a lot of questions that kind of all revolved around one issue. And so I guess we'll summarize it with this. For all of our panelists, what are some of the unique safety concerns and safety advantages of micro-reactors, and why do you feel those particularly confident that micro-reactors can overcome those in ways that maybe previous reactor technologies have left people worried or concerned about nuclear?
Well, this is Jeff Merrifield. I guess as a former regulator, I'll take the first crack at that one. I mean, I think one of the, obviously, if we're using these in more remote areas, there are some who may be concerned, gee, are we really fully cognizant of these designs and how they can be used? And I think the answer to that is yes. I think those who are developing these micro-reactors recognize that those safety and security features are intended to be built into the designs. Some of them will be placed below ground. Some of them will be designed and manufactured in such a way to make a very secure and robust system that could be operated. I think the other advantage of these reactors is obviously the amount of material is fairly small, and so for that reason, even if there were an issue with the design in terms of some kind of an operational concern, the amount of radiation that is contained is quite small, and thus would not have significant impacts on the local community. So a lot of very beneficial aspects to these designs, which regulators like the Canadian Nuclear Safety Commission and the Nuclear Regulatory Commission will look at very closely before they issue licenses for their approval.
Thank you so much for that. And we are pretty much out of time. So does anyone have any final thoughts that they would like to use to wrap up some of the conversations we've had today?
Yeah, this is Tina. I'd just like to reinforce that, we're really at the threshold of being able to use the science that we've learned over the last 30 years about how to fabricate material, even atom by atom, and really how to engineer things to be safe and to be more efficient. I mean, if you just look at planes, we had the biplane, then we had, planes made out of metal, and now we're making planes out of carbon composite. So, this technology can also evolve as quickly and be as efficient and safe.
Thank you so much. And one more thank you to all of our experts and our attendees for your participation in this webinar. We very much appreciate your time, and in return, hope that there were some valuable insights you can take back to your ministries, departments, and organizations. Please enjoy the rest of your day, and we hope to see you again at nice future events. This concludes our webinar.